So if we have two mass which is moving the velocity, say this is mass A, this is mass B, and this is moving with the velocity A, and at the same time it was moving velocity B. And because this is mass, some single mass, let's denote mass of particle A is ma, and mass B, particle B, is mb. And assuming that VA is larger than VB, otherwise nothing will happen, right? Then what will happen is VA and VB will collide. Therefore, there will be some deformation. Okay, and this is mass of A, and this is mass of B. Somebody would think that, hey, then mass of A and the mass of B will be changed. No, mass will conserved. Only the density, local density, is changing. Okay, and this will move. Because this is one mass, this will move with the velocity of some velocity of u, right? And then something which we do not learn very precisely happen, but at least we can agree that after a certain period of time, this mass and this mass will move with a velocity which is not same as VA and which is not same as VB. So I put prime over there. Okay? So what kind of a rule we can use to tackle this problem? Because it involves velocity and mass, and our observation shows that over here at this moment, there will be some force acting to this mass and some force acting to that mass when it compressed. And then because of something that we do not know, these two mass will separate. To be separated, there is another force which will move, which will force this mass from this mass, from this mass to mass. Okay? So in detail, there will be two stages. One is, when I look at this mass, because it is compressed, there would be some force acting on this. Let's call that is P dt. And another stage, this mass will experience another force, R dt, meaning that the mass is pushing the other mass. That two force could be identical or different. Right? What if R dt is 0? That means I am going to collide him, but still, because R dt is 0. R dt means the force to push by him to make me away from him, right? So when R dt is 0, if this is 0, that means plastic. So that is interesting. And if you look at this system, at the whole system, then we can see that all these forces are internal force, equal and opposite. Therefore, I could say, okay, then I can apply principle of impulse and momentum for these two systems from state 1 to 2, and I want to see what's going on from state 1 to 2. Okay? Then I can write the following equation. At state 1, because there is no external force, momentum is conserved. Therefore, I can write momentum, or more precisely speaking, momenta, at state 1 must be same as momenta at state 2. Okay? So what is the momenta at state 1? That is ma va plus mb vv. Okay? Of course, principle of impulse and momentum has to express all the forces acting on that, but that is equal and opposite, therefore that is 0. And momenta at state 2 is ma va prime plus mb vb prime. All right? Okay. And the given is ma, mb. Normally, I do know the mass of A, I do know the mass B, and I do know VA and VB, and I want to find out VA prime and VB prime. And I have only one equation. So that logically means that we need one more equation or constraint, condition. What is it? Where this condition will come out? Obviously, it will come out from this physical observation. Right? Nothing can come out. And this gives us the following relation. That is coefficient of restitution. That is the ratio between RDT and PDT. That makes sense. Right? How much force was exerted when it was compressed, and how much force is induced when it is released. Right? If it is equal, then we call elastic condition. If it is 0, that means integration of RDT, in other words, the force exerted by each two mass when those are released is 0. That means plastic, right? So it's 0, then it is plastic. So we can solve it because we have one constraint. No, we do have one constraint, but it brings another two unknowns, R and P. Okay? To find out what is R and P, we have to look at carefully. And what happened is there is MA, VA in the beginning, and there is the force applied to the mass A, and this will induce MAU, right? And another one I can write is the same relation for mass B. Okay, this is the case when I have MAU plus this will induce this particle MAVA prime. Okay? And I can do the same thing for particle B. And this gives us this coefficient of restitution turns out to be simply VB minus VA and VA prime minus VB prime. Okay? So coefficient of restitution turns out to be concept of the coefficient of restitution is the ratio between these two forces, but because we look at the details applying principle of impulse and momentum, we found out this is simply relative velocity before impact and after impact. And this is always greater than equal to 0 and less than equal to 1, which means that this is positive. That means not only relative, but we do not allow the negative relative velocity, right? So that makes sense because VB minus VA is always positive because VB has to be great. No, VA minus VB is always positive. Otherwise, it will not collide. And after collision, VB prime has to be smaller than VA. Or what kind of velocity we have to use when these two come together? Okay, because we are using coordinate this way, and that one is minus. Therefore, we have VV minus VA has to be, this is relative velocity observed by particle A. So in this case, particle A observed faster velocity than before when it is moving like that, and vice versa. So you have to be very careful to get the relative velocity of each particle before and after collision. Okay? So generally speaking, using this concept, we can solve this problem. Now, what if I have a particle 2, but if this one moves this way, and if this one moves that way, with the momentum of this will collide, and we define that the normal line, the surface, normal to the surface of contact, that is N, and this is tangential direction. And we call this impact line, because there's nothing happen in tangential direction. And we do apply the coefficient of restitution to relative displacement along line N. Relative displacements along line N after impact and before impact. Simply, that resolves every other oblique instance of collision problem. For example, as described in the text, okay, there is a box and the mass, this is moving with some direction of that, and that was moving with momentum, and this is moving momentum V. The only things you have to consider is the velocity in this normal direction. Okay? Velocity in normal direction. And velocity, the coefficient of restitution, as I explained over there, has to be working on this normal direction only. Okay? That's the key thing you have to remember. And next lecture, we will very briefly review what we learned in this lecture, and then we will try to solve some problem. Okay? Okay, see you on coming Monday.